from the Karlsruhe Institute of Technology. Hello. Conducting numerical simulation of idealized cyclones.
Just the talk's just finished, and just get out.
F5 is wrong choice. Presentation. Okay, so thank you for the introduction, and thank you also to the organizers for giving me the opportunity to present my work. I've been studying meteorology for the last 5 years at KIT, and finally a couple of weeks ago I handed in my final thesis, which also was about the adaptive numerical simulation of idealized cyclones, as it is the topic of my talk. But I will not only present results of my diploma thesis, but also further results of a joint research project called Multiple Scales in Fluid Dynamics and Meteorology, which was funded by the German Research Association. And a couple of people contributed to that project, and especially to the results that I will present. And these are Vincent Evelyn and Martin Baumann, who's there today, Leonard Jack and Sarah Jones, and finally Jörn Behrens and Nicole Beisiegel. And Jörn already presented some of my results this morning in the first talk. Okay, so I will start with some aspects concerning the motivation. Then I will introduce basic adaptation techniques, and then I will focus on the choice of an adequate adaptation criterion. Therefore, I will show some numerical results, and finally I will give a short conclusion. Yeah, you probably all know that cyclones, especially tropical cyclones, can be devastating geophysical hazards. If you think about Katrina, 2005, Katrina killed almost 2,000 people, and the costs caused by Katrina by now sum up to $1.6 billion US. Therefore, it is really crucial to have an accurate and early numerical prediction, because then we can warn and evacuate the respective areas. But in order to get to numerical prediction, we need a physical model, and this will probably be an instationary PDE, so therefore we need a discretization. And the challenge is that we're dealing with a multiscale phenomenon. If we look at the pictures underneath, here the cyclone itself is embedded in a large-scale flow, which spans a range of maybe 10,000 kilometers. But the cyclone itself has a diameter of 1 or 2,000 kilometers, and the core of the cyclone is a range of maybe 100 kilometers. But all of these scales are really important, and they do interact with each other. So one way to deal that multi-scale problem is, of course, the use of adaptive techniques. And what I was looking at in my diploma thesis were locally adapted spatial discretizations. And if we have a finite element discretization, we know that the error of the solution depends on the mesh width and the polynomial degree. So there are 3 natural ways to adapt the discretization. The first approach would be to say we start with one finite element with linear ansatz and test functions, and then we can simply decrease the mesh width. That's the so-called H-adaptivity. Or we could equally increase the polynomial degree of the ansatz and test functions. That's the so-called P-adaptivity. Or we could simply move our degrees of freedom. That's the R-adaptivity. And in my work, I was only looking at H-adaptivity. And there we saw if we have an H-adapted mesh, this will lead to an artificial asymmetry in the vortex profile, as you can see on this picture here. So the black solid line is supposed to be a symmetry axis, but we see it's not symmetric anymore. Asymmetric vorticity profiles also appear in real nature, but then they are always linked to vertical instabilities, vertical shear winds, and this will lead to a weakening and to a weakening of the cyclone and the deformation of the storm's track. The question we posed is, what happens if we have an artificially induced asymmetry? Will this lead to the same results? Will we have an influence on the storm's track and its intensity? That's what Jörn this morning already showed. And therefore we did some tests of vortices that move with a constant background velocity of 10 meters per second towards a frontier in grid resolution under different angles. So here it just moves ahead the frontier, here different angles where it moves towards the frontier. And to check the influence, we had a look at the storm track, which is being computed as a weighted barycenter of vorticity, the rotation of the velocity field. And to check the intensity, we computed the kinetic energy of the vortex. To ensure that the results do not depend on a specific model or a specific discretization, we did these experiments with two different models. First model is a continuous Galerkin model based on the Navier-Stokes equations, and the second model is a discontinuous model based on the shallow water equations. Don't want to go into many details, but the CG code is called HighFlow, and it's open source by a working group of Hövelin at Karlsruhe Institute of Technology. We use it to simulate the two-dimensional Navier-Stokes equations, and for the discretization in space, again, we have a continuous Galerkin method with quadratic elements with Taylor-Hood ansatz and test functions. So it means we have bilinear functions for pressure and biquadratic functions for the velocity components. And discretization in time, we use an implicit continuous Galerkin-Petrov method. And the other model we used was a model of Björn Behren's working group, and it's called Stormflash. We used it to simulate the shallow water equations, and for the discretization in space, we have a discontinuous Galerkin method with triangles with linear ansatz and test functions, and the discretization in time is an explicit two-step Kronig-Kutter method of order 2. Okay, so some results. I will only show you results of the simulations with HighFlow, as we got almost the same results with the other code, so the results did not depend on the discretization or the model itself. So here on the left we see a vortex that starts in a fine mesh and now moves with a constant velocity towards the frontier in grid resolution. And on the right side we see the rate of energy loss of the vortex, and here's the distance in x direction, so how far did the vortex move. And the green line represents the energy loss on a respective uniform mesh with the coarse grid resolution, and the turquoise line shows the energy loss rate as it would be on a uniform fine mesh. And the blue line now is the energy loss on this adapted mesh. And we see at the beginning our vortex just behaves like it would do on a uniform fine mesh. Then there's the transition area where it touches the frontier and moves ahead, and finally this line again, here it's completely in the coarse mesh again. Here it's completely in the fine mesh, transition, and completely in the coarse mesh. And we see after the transition area, the energy loss rate is parallel to the loss rate in the coarse mesh, so this is a good result because we do not have any additional effect of the frontier in grid resolution. And it's exactly the same for the other way around. At the beginning we have the energy loss as it would be on a coarse mesh and transition area, and then it's parallel to the loss of the respective fine reference run. So next thing we wanted to check was the storm track. We start in the fine area. We start with almost no deflection, then there's the transition area, and then we have a bigger deflection, but of course this is due to the fact that we have a coarse grid. So here this is no additional effect too. If we go the other way around, we start on a coarse mesh. Again, we start with a deflection of 2 to 3 kilometers, which is quite small compared to the mesh width and the diameter of the cyclone. Then we have a transition area, and the deflection gets a lot bigger. And in the fine mesh, we still have really big deflections, so this is not so promising. So we could have expected that the fine mesh is able to damp the deflection, the fluctuations. And to check that the storm track does not diverge, we did some long distance runs where the vortex moves almost 4,000 kilometers, and we see after some time the fine mesh is able to damp the fluctuations and the storm track converges after some time. But still we have a deflection of approximately 5 or 4 kilometers, and so after all we have to admit we have an influence on the storm track, but still the deflection is very small. Because now it moved 4,000 kilometers already, and yeah?
Teresa, if you say that there is still a deflection, that could be an error that was kind of accumulated in the coarse region. So you cannot kind of correct the error that was initially there, even if it's still bouncing around.
Yeah.
If you have the error from the coarse region, why do you think you can get rid of it?
Now the question was if the storm track diverges, and it does not diverge. That's what we wanted to check. Of course, it will not go back to its initial track or the track it was supposed to have.
Yeah, so that's what you see here. The
Yeah.
tail becomes, so you have less bouncing,
Yeah.
but obviously the wrong result because the error was there already when you entered the fine area. Isn't that true?
We didn't, for this investigation, we didn't see the reference run on the cost grid. We saw that for the energy loss, but not for the position prediction. And as I remember right, we did such tests as well on uniform course measures, and there was not such a big deflection.
Well, if you would,
So
do,
I don't think these deflections we saw in the very first interval already are there because of this boundary. No, because of this interface between two mesh resolutions. I think the coarse mesh uniform simulation was without
Yeah. It almost had
fluctuation,
no.
right? So therefore, I think
fluctuation.
everything we see here is really due to this change of
to the
resolution.
interface, okay.
It seems like the error is just some small fraction of the grid
Yeah,
length. So
it's
this is
pretty
very
good.
small.
It's quite small. Better.
200 kilometers.
200 kilometer storm, just
Mesh space,
That's
that's
mesh.
H, right? So
25 kilometers mesh. Very small.
I wouldn't think you could do a whole lot better.
Mind you, you're not even committing an amazing amount of error on the coarse mesh. So
Yeah.
there's a question like about how much you've really gained because you were doing pretty well with the coarse mesh.
Probably. We just wanted to look here whether there is some extra influence. So if there is some reason we have to use a fine resolution somewhere in the domain, will this cause just the presence of a fine nest, for instance, will this add extra problems here? And I think we tried to figure that out by this simple test. And we have a good answer, no. But this is only for this series of tests, I think.
You'd want to be pretty confident in your forecast though if your error bars for your evacuation area weren't bigger than 5 kilometers.
The cyclone is like 200 kilometers wide. 5 kilometers doesn't make a difference, right?
I just had a quick comment. I mean, I agree that this is a sort of a very nice test. And of course, it would be a sufficient test to show that you don't, that somehow your results look good if you go from a coarse grid to a fine grid. But really, the problem is being able to track, you would be tracking that vortex on a fine grid. And you'd want to see the vortex, how the solution, I mean, that would be a sort of a more relaxed test, but maybe a more realistic.
If
Do you see-
you can't technically use a dynamic measure depth,
Right, exactly.
Some packages maybe can't at all. So you can, in the first step, optimize a mesh, and then maybe this will move into regions of fine resolution, or next to it, or close to it, and so maybe there
I
are
mean, 'cause
technical
there's even
restrictions
issues,
if
in dynamic
can't
meshing,
just do-
are you able to transfer the information in a way that doesn't lose accuracy? So there's certainly issues there as well. But
Yeah.
that would be sort of ideally what you would be doing in this case. And so in a sense, yeah.
Okay. So, yeah. So the next question then, so we checked and decided, okay, H adaptivity works for what we are doing because we were only using static adaptivity. So we had these issues that we come from a coarse mesh to a fine or the other way around. And we summed it up and say, okay, we can make use of H adaptivity. But then the next question was, how do we control adaptivity? How do we choose an adequate adaptation criterion? And the first approach we investigated was a classic a posteriori error estimator approach, where we control adaptivity due to local contributions to a total error of the solution in a global norm. And the second approach was we're interested in an error again, but not in the error in the solution, but in the error of a specific goal functional. And again, then adaptivity can be controlled by local contributions to that total a posteriori error in the specific goal functional. And the last approach would be to say we want to refine everywhere where the physical phenomenon takes place. For example, we know cyclone always has a low pressure core, so let's say refine everywhere where the pressure is low. And all these three approaches, we wanted to compare them with regard to the efficiency of the resulting mesh, which was defined as a ratio of an error and the costs that were required. As a benchmark problem, we used the interaction of two cyclones with each other because this has been an interesting problem in meteorology for almost 100 years now. Here we see different examples of real interaction modes of different cyclones in the western North Pacific region, and we see that there are different types of interaction. For example, in the first example, both cyclones first orbit a common center and then move apart. In the next case, they merge and become one cyclone, and here they orbit each other and then finally move apart. So this is classic Fujiwara effect. And meanwhile, it has been found out that the interaction is highly sensitive to the initial distance of the two vortices. And the numerical simulation is not only sensitive to the initial distance, but also to the viscosity and the mesh width. So we see here an example of the dependency on the mesh width. We know how the solution should look like. They orbit each other and then finally move apart. And only the finest mesh is able to compute that physical solution that really should result. If we have bigger mesh widths, then the two storms will merge and become one cyclone. So this is a bifurcation problem, and the existence of such a binary system of two cyclones will make the predictability of a storm track very difficult, as it has been shown. So the model scenario, now we have two vortices, two vortex profiles with an initial distance of 400 kilometers, which is approximately the critical distance. If the initial distance is a little smaller, then they will immediately merge and become one cyclone. And here for these tests we used high flow with the Navier-Stokes equations again on quadratic elements, Taylor-Hood elements, and again a continuous Galerkin-Petrov time-scaling scheme. And again we used H adaptivity, and to control adaptivity we used the fixed mesh fraction strategy that always refines a certain percentage of cells with high indicator values in every adaptation cycle. But now we have to find an appropriate adaptation indicator, which has to be designed for every different approach, for the a posteriori approach, the goal-oriented approach, and also for the physical approach. In the first case, for the a posteriori error estimators, we know that the error of the solution in a specific norm is smaller or equal the sum over the local contributions of an error indicator, and we used a residual error indicator for both the Navier-Stokes equations and the Poisson equation. So the question was again, how do we choose our adaptation indicator for the strategy we use? The strategy is designed to equilibrate indicator values. So in this case, we can simply set adaptation indicator equals error indicator, and then we will equilibrate the error indicator values over the adaptation cycles. For the goal-oriented approach, it's very similar. Here we're interested in the error in a goal functional, and that also has an upper bound that depends on the sum of local contributions to the total error, and we made use of the so-called dual-weighted residual error estimator according to Becker and Ranacher. Here we have a primal problem, and we can derive a dual adjoint problem with the solution Z, which represents the sensitivity with regard to the error in the goal functional. And the resulting error indicator reads the following. We have residuals that depend on a cell residual and edge jump terms. And these residual values are weighted with the sensitivity information, which depends on the interpolation error of the dual solution. But the problem is now that we do not know the dual solution. The exact solution is unknown, but as we're interested in the interpolation error, we can replace the solution with patchwise interpolation into higher order finite element space, and therefore look at the interpolation error of the known discrete solution of Z. So if you start, for example, with 4 bilinear finite elements, this can easily be seen as 1 biquadratic element, so this would be the interpolation in the higher order. So in 1 dimension, this would be 2 linear elements, and this would be 1 quadratic element, and the green shaped area now represents the interpolation error. And so the resulting error indicator only depends on the discrete solution of the primal problem and the discrete solution of the dual problem, and this is something we can evaluate. We still don't know what goal functional to choose, and for our application we choose the error in the storm position, error with respect to an a priori storm position that we know because we have a high resolution reference run after 96 hours, and we used the integral over the vorticity after 96 hours of our run integrated over the core of the storm of the reference run. And in that case, again, we can simply set adaptation indicator equals error indicator again. For the physical approaches, it is more complicated because we used that strategy that was designed to equilibrate indicator values, but our physical criterion itself will not depend on the mesh width. If we think about the pressure again, we can refine everywhere where the pressure is low, but in the next adaptation cycle, pressure is still low at the same domain, and we would refine the same domain every time. So what we did, we designed our own adaptation indicator for this physical criteria that forces an H dependency of the respective physical quantity. So here is the resulting indicator. It's a mesh width to the power of a specific parameter beta times the cell value, cell average of the physical quantity. Another question is, how do we choose a good beta? And here we show different resulting meshes with different choices of beta. The physical quantity now is the square of vorticity, and for a small beta we get an adapted area which is localized around the storm core, and we have a high number of different adaptation levels in one mesh, and the bigger beta gets, the broader gets the area that has been adapted, and the fewer adaptation levels we have between the highest and coarsest grid resolution. Yeah, the problem is that beta does not only depend on the indicator but also on the problem we want to simulate. So we, for our application, did a parameter study to find the best choice of beta, and the results for the vorticity indicator showed that beta equals 16 is the best choice for the vorticity indicator, and for an energy indicator based on the kinetic energy, best choice of beta was 2. So finally, some numerical results. On the x-axis we see the number of degrees of freedom, and on the y-axis we see the error in the storm position to the reference position. That's logarithmic, and I will start with the black solid line. This is the uniform run. We see here at the beginning, for small numbers of degrees of freedom, we have huge errors in storm position. This means that we are computing the wrong physical problem. We saw that this was a bifurcation problem. In all these simulations with 1,000 kilometers error in storm position, the two storms merge and become one cyclone. So this is actually the wrong solution. And here it gets better, and finally, for huge numbers of degrees of freedom, we are almost 1 kilometer error in storm position. And all the applied indicators lead to more efficient meshes than the uniform runs. So this is the good news. And the best results could be achieved with the dual-weighted residual error estimator. Here for only problem sizes of 13,000 degrees of freedom, we have an error of 4 kilometers. So this is quite a good result. And surprising is that with the physical indicators, vorticity and energy, we were also able to produce better results than with the goal-oriented approach. So this is really promising, but it depends on the optimal choice of beta. At the same time, we were also able to produce equally bad results with the physical criteria. We also had results that were worse than the uniform runs with the wrong choice of beta. Yeah, but now let's have a look at the costs that were required to get to the accuracy. For the residual error and the physical indicators, it is easy to evaluate indicators because we can evaluate them at arbitrary time steps, and the additional storage required is limited by 1 floating point number per cell. So there's no big effort. It's more complicated, of course, for the dual-weighted residual error indicator. That's what you've seen already. We have to compute the primal problem once in time. Then we have to store the complete primal problem, because based on the primal problem, we solve the dual problem backward in time. So we have big storage requirements because we have to save the complete primal solution, and then the additional effort to compute the dual problem backward in time. So talking about the efficiency, we saw, well, the error. All indicators led to a more efficient mesh than the uniform mesh, and best results were achieved with the goal-oriented approach. Really good results were also achieved with the physical indicators, what was surprising, but this really depended on the choice of beta. And for the physical indicators, then we had, of course, an additional effort to find the optimal beta. And so first of all, we had to define what optimal beta was supposed to fulfill. And during runtime, the highest computational cost and highest additional storage required we had for the goal-oriented approach. As a conclusion, well, first, again, I checked H adaptivity, and we saw we have no additional influence on the intensity of the storm and a minor influence on the storm track. But we did not only do that H adaptivity test, we also did tests with R adaptivity, and at that point I want to advertise a poster we brought. You can see some results of R adaptive techniques and also of goal-oriented adaptation of the time discretization. And you can see that at the poster outside. And to check the different adaptation criteria, we saw that for this scenario that we were looking at, which is really somehow a baby problem, all indicators led to a more efficient mesh than uniform meshes. And there were big differences in computational costs and the required storage. As an outlook, first we want to check if beta maybe is generic. This would facilitate a lot. We could further do more experiments with the physical criteria. And finally, we would like to translate our approaches to three-dimensional and more realistic scenarios, maybe with a frontal zone, maybe with a third vortex, or with vortices of different strength, and maybe also look at humidity effects. And so there's still a lot of work to do. So I thank you for your attention. And
I would expect that when you're using the dual goal-based error measure, that the results for that would improve if you adapted less frequently, because then it's sort of looking forward in time to the end of the time window and making sure that the mesh is good for that entire window. So did you experiment with changing the frequency of the adapts? Calculations.
It was actually his work, the goal-oriented stuff, but we also did tests with different goal functionals that did not depend on the on the continuous solution or the reference solution, and there we did tests with different frequencies.
We did kind of the extreme case of what you just
Right.
explained.
Yeah.
Do it in each single time step, and this is even a name. It's called the local dual-weighted precision method. Local in time. That's the meaning. And it turns out that for certain applications, the sensitivity that you get by the solution of the dual problem is very high for certain effects that are started. So perturbations can be started or introduced at very early times, but they influence your goal at the end of time or very, very late. And if you restrict yourself with your computation of this sensitivity information to small subsets of the time span, you won't get any information about later time influence. And in this case, it was really the case that perturbations at the initial time had a big influence, and which were located far away from the two vortices sometimes, to the final position of the storm. So I think the answer is it's application dependent, of course. For some cases, it's probably not the big problem.
It does mean that
But here, it would.
So your conclusions from this plot of the different errors would change if you changed the frequency of the adapts, though, I think.
I'm sure about that, yeah.
But hang on, I think you've just conflated two different things, because you made an assumption that you solved the dual problem only ever over the course of one adapt. And actually, those are two questions, right? There's a question of how long do you run your dual problem for, and the question of how frequently do you adapt, because there's no law that says that you can't adapt at several points inside a dual problem run. So if you just think about tracking a cyclone, I might solve the whole dual problem, but still keep moving the adapted region at various points, and I still get an error measure out of my dual problem, right? It still works.
I don't know anything who does that. Bob has a question.
So you're comparing with a uniform grid over the entire domain. In hurricane forecasting, going back almost 20 years, the way that people have kind of done things, and recognizing that a hurricane is a well-defined system, is just to kind of have a moving mesh. So it's not a terribly intelligent or careful approach, but you have a region centered around the lowest pressure in the domain that's at a fairly high resolution. And so unlike here, where you're actually kind of refining locally and looking at structures, you just have this moving mesh. In some ways, that might be the kind of the base to compare against, is just this very naive first step towards adaptivity. How much more do you get with the much more elaborate and sophisticated and thoughtful machinery that you're using? If you compared the efficiencies per degree of freedom with something, and I suspect you could do this already with your code, where instead of having kind of a highly structured, you just have a really naive big square box around the middle of the vortex that you move around with the vortex.
We didn't compare it, no?
Yes, with this software we didn't do a series of tests and so on, but a colleague, Leon Hacek, he was also part of this project. It was just running some tests with Icon, and they did forecasts for the cyclones, and they used nesting techniques. And he talked to people and asked, so in this case, how would you choose your nest, and how many kilometers should it be, and so on. And he did what was told to him, and he did a very good series of tests, and he found out that at some specific situations there are big influences on the outer part, which you would have not expected to happen, because it's a quite big domain. But it depends on the large scale structures and influence with other cyclones and so on. And therefore, still in the case where you have nests and you move it, there's still a question: how should the nest look like? How big should it be? Is it symmetrical? The storm looks symmetrical, so the mesh must also be the nesting part must be maybe
I think they usually make it symmetric just because they don't put much thought into what should you just want some high resolution in a broad area.
Yeah. So from my point of view, this could be the technical. Who said so? That could be a nesting technique. Could be what you do also after you did your error measure and a posteriori error estimation. So we did a refinement of single cells, but you could also reduce this indicator information and ask the question, how should my nest look like, and where should I put it, and yeah. So maybe yeah.
I just think in terms of kind of demonstrating the value of the technique, that using the right baseline, can you get most of the benefit just by doing something naive? You know, showing where you really do benefit from being thoughtful about where you adapt might be a way to kind of sell what you're doing to people who say, you know, we've been doing this forever.
Put the grid where the
Just throw a grid where the cyclone is.
Well, and that's proven to be pretty successful.
And
so,
absolutely.
Yeah, I think it is important to demonstrate that you can do better than that.
But these nested tropical cyclone models, they were developed when the models couldn't resolve tropical cyclones at all. They couldn't support a 100-kilometer mesh. Now we're at a stage where the global models, running at 20 or so kilometer mesh spacing, are resolving tropical cyclones, and it turns out that they are doing the best track forecasts. They're beating the hurricane models, which have these nests that go down to a couple kilometers or even less in some cases. So increasing the resolution in our current generation of models past a few tens of kilometers mesh spacing is not gaining us hardly anything. At least that's the evidence so far.
But you're saying that it's the
Track
global?
Track forecasting.
Coupling with the ocean.
No, intensity forecasting is even a sadder state. We don't really understand. Our models just do poorly. All our models do very poorly on intensity forecasting. So just going to higher resolution for the full problem doesn't seem to be helping right now.
But you were saying it's a global.
Maybe one comment after beer. It's a very nice talk, but I agree that the global model are doing well, even the operational model. And I think that the example for the motivation of the work, giving Katrina as an example, is a good because of the number of casualties and the number of damage, but it was not a forecast problem.
Yeah, okay.
It was something else.
It was a great forecast.
Great forecast. We were so lucky in that case that the forecast was just dead on, so that when people came back and said what went wrong and whose head should roll, there were no meteorologists.
Thanks, Bob.
Any other questions or comments?
I think we should severely embarrass the speaker by pointing out that that is Teresa Beck's master's project, which is just tied down a room full of professionals who've been doing this for years, which I think is an exceptional achievement.
Okay, let's thank the speaker again.